Hello. I believe some of you have already met me. My name is Eugene, a member of the Humanist Association of Ghana. And today I'll be taking you on a journey from Accra to the cosmos. Largely what we'll be tracking are the chief historical events that shed light on where we are in the universe and the individuals who contributed towards it. I want us to largely focus on the fact that this is a work in progress and there's still a lot to be learned. Compared to us, we are puny when you take into consideration the giant universe. So you have to really take into consideration the fact that this is still a work in progress. There's a lot to be learned. Maybe some of you here might be interested in taking on a career in astronomy and then contributing to our understanding of the world. All right. So I'm sure you all know this man. Is there any individual here who doesn't know him? Okay, so that is Albert Kofi Einstein. Although he didn't use the Kofi, it's safe to say that we know he's a Kofi because he was born on Friday. Anyway, so let's begin with one of, I think, the most profound quotes from Einstein that I really love. That is, "One thing I have learned in a long life, that all our science measured against reality is primitive and childlike, and yet it is the most precious thing we have." I just want us to understand that really we are at the beginning of our quest to comprehend the world. And there are a great many things that we still do not fully understand. But we have come far, and we need to celebrate how far we've come and still recognize that there's a lot that we still need to understand. This is not that we will be filled with hubris and say, oh, we figured it all out. That's not what this is about. This is just to tell us that there's a great deal that we need to still probe into. Now, I believe you can see this child here. She symbolizes our insatiable need to understand or to know. This is very clear when you see a child, a very little child, asking the parent, "Mommy, what is this? What is that? What's the name of this? Why does this happen? Why is there day? Why is there night?" I suspect a great deal of us lose this because we are soon told that, hey, stop asking these questions. But this behavior is a uniquely human thing. Not many animals share this trait with us, that they want to understand the world. Then there's our rich set of languages that we've evolved over the course of civilization to help us better explain ideas to each other and convey meaning and understanding and then cooperate to carry out one activity or the other. No other animal on this planet has such a refined language as we do. And again, we are met with this rather interesting story that I'm sure most of you are aware of. That is trying to track, according to this particular account, human beings were created hungry. And hungry for what? Not for food per se, not for shelter per se, but hungry to know. And they had to know, and they needed to know. And we are told that the current state of our universe is because some individuals wanted badly to know. Very few animals share this particular trait with us. Again, our need to know reflects itself in the various instruments we create, from a plow to a telescope to a microscope to a computer. They are all ways by which we are trying to satisfy our need to comprehend the world. Now, I want you to pay attention to this bird, right? If you look at the plumage of this bird, it is very different from this other bird, right? Okay. The creature you are looking at, this very one, is what we call the cuckoo bird. And I bring it here for your attention because it's a rather curious bird, in the sense that it doesn't build its own nest, this bird, the cuckoo bird. It doesn't. I'm sure if you ask it, it wouldn't know how to do it. But it does this rather interesting thing, where instead of building its own nest, it will rather look for the nest of another species, another bird species, take an egg out of the nest, and then lay its egg in that nest, and then fly off. Right? This is a rather bizarre behavior. But then that's what they do, this cuckoo bird. So the curious thing about their young is also that they will quickly hatch, and then guess what? They'll toss all the eggs out of the nest. Is this a fair thing? Okay. I'm sure you know it's not fair. But that's what these birds do. And time again, that's what they consistently do. So after they hatch and toss all the eggs out, they'll start crying. And then that's how birds signal that they need food. So this other bird from another species would now go look for grubs and then feed it. And to be growing very rapidly. You can tell that it's much larger than this parent bird that's feeding it. And this is the behavior of the cuckoo bird. But the curious thing about this behavior is this. These birds don't go to cuckoo bird school where they are taught how to behave as cuckoo bird. When it grows up and becomes female and then it's time to lay its own eggs, it will carry out this same set of behavior, this behavioral pattern. As to look for another bird's nest, take an egg out and then lay its egg in it. I bring this to your attention because we have to understand that we are also part of the universe we live in, and that as human beings, there are innate drives in us that nobody teaches us. And I want to make the case that the need to know is hardwired into our genes. It's not something human beings are taught. They have to know, they want to know. So much so that some people even prefer conspiracy theory to you saying, I don't know what is happening here. It's a serious drive. And another case in point is also that plants also, for one reason or the other, need to move towards the sunlight. But in the case of a plant, I think you can understand, and pardon them for that. But no plant is taught this in plant school. Right? The case I'm making here is that animals have a unique set of behavioral patterns, motivations, and drives that are unique to them, and they only them. And human beings have a unique drive, and that is the drive to know. So you can see that a spider will weave a web, fishes know how to fly, swim, and then birds fly, and I'm sure you know what he's doing. He's thinking, doing the uniquely human thing, right? Although he's doing that on the toilet seat, but he's still doing that nonetheless. That's a uniquely human trait. Now, our need to comprehend the world usually presents itself in two implicit ways of looking at the world, which is, when you look out into the world, you are always asking the question, why? Or you're asking the question, how? There's a radical difference between these two ways of looking at the world, right? So there's what I call the purpose-motivated view on the world, and then the pattern-motivated view on the world, right? These are two ways of seeing things in the world, where when you see an item, you're asking, to what end? What is it trying to achieve? What is the goal? And then we have the pattern-motivated view on the world, which is a question about, what are the rules here? What are the unbroken rules that these objects need to follow, right? And these are the two chief ways of looking at the world. So look. A case in point would be, if you adopt the purpose view on the world, a typical question that will occur to you is, what is the purpose of the sun? Or what is the purpose of the moon? Or even more interestingly, why do stones fall? Or even this object, why will it fall? If you adapt the purpose-motivated view on the world, you will be forced to come up with an explanation. And if you don't have one, you have to forge one. So in the case of the sun, you are told that its purpose is to shine or to rule the day. Again, because you want an answer to the question, purpose. Then the other question being, what is the purpose of the moon? You are told to shine during the night or to rule the night. And why do objects fall? In this particular case, interestingly, Aristotle told us that objects move towards their homes. And it is the home of stone to be on the floor, right? So stones are always trying to get back home. That's why stones fall. And you answer things this way because you are purpose motivated. But then another view, which I think is the youngest view. We are told historically that this view was championed first by the Greek lover of knowledge, Thales, who's really championed the idea that instead of focusing too much on what purposes things are trying to meet, you can focus on what rules are always recurring, or what patterns are always recurring, that we can try to look at the system very carefully, decipher it, and then answer those questions. Because maybe the purpose of things will be a difficult question, but what are they doing will be a much more easy question. So you could ask, what is the sun? What powers the sun? And then we now know it is an interesting type of fire, and human beings achieve this fire close to the end of the Second World War, which is what we call a nuclear reaction at the center of the sun. Now, and mind you, this is because we know how to do this particular thing, nuclear reaction. Now, for the first time in human history, we now have the means to wipe out the whole civilization. Interesting. Now, on the question of why does the moon shine, upon studying the issue very carefully, we have understood that it is not shining. The moon is not really shining. It's only reflecting light from some other object that's actually doing the shining. And why do stones fall? From a pattern-motivated view on the world, you understand that it's always because they are attracted to our home planet, which is the Earth. Let me give you another interesting example of a pattern-based view on the world. You are to imagine two kids at a well, right? Bear with me. I don't expect you to come up with the answer for this, but if you give it some careful consideration, you'll come up with the answer. You are to imagine two kids at a well, right? And then one kid says to the other kid, "How deep do you think this well is?" And then the other kid reaches for a stone and then asks the kid who asked the question in the first place that, "Do you have a watch?" Right? Is being employed here to answer the question. Because whatever it is about patterns. It's about how time can tell you something about depth, which is a pattern that is not broken by objects that are falling. And this is what is being exploited by. You can think about it a little further. Another interesting case where pattern or a pattern-motivated view on the world props its head is when interesting problem. So a young lady moves over to see the pyramids, and then she's awestruck by the pyramids, right? And while she's in the shadow of the pyramid, asks the question, I know this doesn't occur to many of us. How tall do you think, or how high do you think this pyramid is? So she's wondering, the tour guide she's with doesn't also know the answer. Then an idea comes to mind. She takes a stick, sticks it into the sand upright, and then she comes up with the answer for the height of the pyramid. What deep structure about relationship between sticks and possibly shadows gives you an insight into the height of other items? In this case, a pyramid. I just want you to consider those two problems only in the sense that I want you to come to some understanding that there are rules by which the world unfolds. And if we tap into those rules, we'll be able to penetrate deep questions about how the world really, really works. Who can tell me what's wrong with this picture? Anyone? You can take a stab at it anyway. Okay, you. Good. Wonderful. So what it's alluding to by saying scale is simply the idea that we know what an elephant looks like. In fact, we have a rough idea about how large an elephant is, and we have a rough idea about how large an apple is. And they are not the same size, right? They are not to the same scale. If they were to the same scale, one will be much smaller than the other. right? So I want us to really have at the back of our minds during this journey that scale matters. If you see a picture over here and it looks like, oh, maybe it's a couple of inches big, it doesn't mean the universe is a couple of inches big. I know individuals who, when you ask them, how big do you suppose the sun is, they will close one eye and then stick a finger out and then see whether they can block the sun with that finger. Oh, I suppose it's this big, and show you that is, the sun is this big. Really, you have to really understand that scale has to always be considered, that what you see doesn't always betray its real size. So that has to always be operating at the back of your mind. So our journey begins. The very first problem that we had to really solve when it comes to our place in the universe is this home planet, or this place we find ourselves. What is the shape of it? Is it flat? Anyone at a beach would think that it is flat, that it expands infinitely into the infinite, into infinity, right? But then if you observe this curious thing, which was first noted by the Greeks, because the Greeks were also a ship-faring civilization. So, I mean, they had ships going off to distant locations, and if you're at the shore, you notice this rather curious event, which is after a while, after the ships have sailed away from you, you will notice that the hull of the ship, which is the bottom part of the ship, is no longer within sight. Why? You can either say, oh, maybe if you go further, you start to drown. That is why you're seeing this object. But if the ship comes back to the shore and you ask them, did you guys drown? They'll say no. So what is actually happening? Now, this effect is explained because the earth is not flat. It's actually a ball. And over a certain distance, roughly 4 kilometers, you get over the bulge, and then the bottom part of whatever object you're seeing is below the horizon. So it will eclipse your view, so you can't see it. So this was one of the first sightings that told us that the ball on which we are on, the place we are on is not flat and floating on water, but it's actually spherical. I know many of you know this, but largely because a great many of you have been indoctrinated in school and had to memorize it for one exam or the other. But these are some of the ways you can prove to somebody who tells you that, this whole round ball business, I don't think it is the case. This is one of the interesting observations you can point them at. Then there's also this other curious observation about the shadow of the earth on the moon during a lunar eclipse. Now, the great explorer, Christopher Columbus, was asked by his shipmate whether he was sure that the alternative path he wanted to use towards the Indies, right, to partake in the spice trade, he wanted to use the west route. Well, he was asked because he suspected the earth is a ball, so he felt you could move in the west direction and still appear at the other end of the ball. So he was asked by a shipmate, are you sure that the earth is a ball? Isn't it the case that it's flat and at some point we'll go over the ocean and then we will die? Because that used to be the idea. But then his reply was, I have faith in the shadow of the earth on the moon. That is to say, whenever there's a light source and you stick an object in front of the light source, you are most likely going to get, I can get a shadow on there, but you're most likely going to get a shadow in a rough shape as the object that is sitting in the path of the light. And during a lunar eclipse, you get this wonderful alignment where there's the sun on the one hand, there's the earth in the middle, and then the moon to the far end. That forms a screen. And every time you see a lunar eclipse, it always has this curve. Always. Always. So this curve will come this way, come that way, come this way, and sweep across the surface, right? And then the other end will be reducing this way, and then to be shining, to be shining, to be shining, and shining, and fade away. So it tells you that the whole object itself is spherical and swept across the face of the object. And this was one of the key evidence that told us the shape of the earth that we are on, although you and I clearly see it to be flat. The other thing for consideration after we realize that the earth itself is round is the moon. What about it? is it not just a plate hanging in the sky, a flat plate hanging in the sky? I mean, because you can't tell it's spherical. And I mean, who's to say it's not a flat plate? After all, we can always cover the sun with our thumb. So isn't that the size of the sun? But the interesting observation that was made is that you always notice that the moon goes through what we call the phases, the various phases of the moon, right? This, I'm sure you've all seen this, where there's a full moon, there's a half moon, a crescent, a new moon, all of that, right? After careful consideration, the Greeks thought that if the moon is a sphere and is being lit by the sun, then at all points in time, half of it is always going to be lit and the other half is going to be dark. But depending on where you are on the earth, if you are here and you look at it, you see 50-50, so that you call it half, right? If you are here, this side of the earth, and you look at it, you're only seeing the dark side, so you say it's a new moon, it's only darkness. If you are here and you look at this side, you see the full lit end of the moon, and you call it full moon. And similarly, if you are looking at it at oblique angles, you're only seeing portions of it. So the waning and waxing of the moon was the clear evidence for the fact that it's spherical, and that the difference, what you see over the course of a month, is due to the motion of the moon around the earth and its relative position. So if it's a 90-degree angle, half. If it's a, so I say 0-degree angle, you are seeing no moon. 180, you are seeing full moon. And that's how we understood that the moon itself is also a spherical object. Now, when you and I was asking earlier, I don't know how many of you were available then, but how many of you have seen a planet before? Okay, you are out. You always see planets. Who has? Okay, I'm sure. So the interesting thing is this, right? When you see a planet in the night sky, you don't go immediately like, oh yeah, I see you, you're a planet. That's not what you go like. Rather, you see a dot in the sky that looks much like a star. So what betrays it as a planet is not the fact that it's shining and looks like a dot. What betrays it as a planet is that if you kept looking at it over the course of months, you notice it's shifting in the night sky. So let me use this, the laser as an example. So ordinarily you see something like this as a planet, and over the course of a month it will be shifting. So look at each background, this background, as the background of the sky. And the way we know there's a background like this in the sky is because there's a star combination in that background called a constellation. So there will be a constellation in this square, there will be a constellation here, there will be a constellation there again, there will be another constellation. So you notice a planet like Jupiter first being in this constellation, let's say constellation A, or star picture A. And then next 2 weeks, you look at that same, star again and say, it's here now. What's happening? And then you check again, it's here now. And you check again, it's here now. And then it will sweep its way through all the zodiac symbols, which are patterns of stars, and then return again. And that's what you would notice about some of the stars. The rest of the stars, the one you and I call stars, don't move this way. They don't shift against the background. So a star is a Greek word for wanderer. A planet is a Greek word for wanderer, to be wandering around. So they didn't know that they were worlds. That's not what the Greeks knew. What they knew was that there were a certain set of stars that kept changing across the night background. They knew roughly 5 of them at the time. Because to see more than 5, you would need something better than the human eye to do that. Now, most Greeks studied this thing very seriously. Their lives depended on it. Because unlike the modern day, they didn't have a calendar. They didn't have a timepiece, and neither did they have a compass. So it was hard for them to move around. It's hard for you to know where you're going if you don't have a compass. Now Google Earth helps us with that. It's hard to know what time of year we are in without a calendar, but then you could. But the way they did it was to look at the night sky and then study what stars they were seeing, because at every point in the year you see a certain set of stars, right? You get me? The sun will be at a certain location in the night sky. And that's what they used to tell. After the Greeks studied this for a long time, so now they could split the difference between a star and then planets, because they knew that planets are the ones that are changing, stars are fixed in the background. And then the Greeks couldn't get their head around the idea that the Earth spins, right? For them, the Earth doesn't spin. Because I'm sure you and I are aware, if it were spinning, we would know, wouldn't we? It is like saying if you're in a car and the car is moving, you wouldn't know. You would know, right? So the Greeks thought, this is a ball, they got that one right. They knew that there were stars that were changing across the background. They got that one right. Right? But for them, they couldn't say that the Earth was spinning. For them, the Earth was fixed and the center of all of this. Because after all, when you look into the night sky, you are the center of your observation and everything is in the background. Right? So their view was that the Earth is in the center, this one, and then the planets are arranged in concentric, for some strange reason, crystal spheres around the Earth like that, in nested crystal spheres. So it's actually like a circle in a circle in a circle, but we've cut the top half so that you can actually see what they were thinking about at the time. Okay, so this was a prevailing Greek idea for close to, I think, 1,400 years. And most people believe that this is how the world worked. And there isn't any good reason to suspect otherwise, right? Because even the fact that it's a ball self, you didn't know that. You thought it was flat to that observation. So how much more the picture, your impression of the world, if all you had to go on was just the Earth and then what you could observe. So they thought it was like this. And this idea was championed by the mathematician who studied at the Library of Alexandria. So we are talking about somewhere, I think 300 years after Jesus. It was championed by the Greek mathematician Ptolemy. So he came up with this beautiful mathematical system. You could tell when an eclipse will occur. You could tell when this planet will be in a particular position. And this was very vital, mind you, at the time. Because back then they thought if you can tell what will happen in the future, then you can predict events to come, right? So there was this other astronomer called Tycho Brahe, who suspected that the plague that went through Europe and killed a great many people in Europe was predicted because of a certain alignment between two stars in the night sky. So this was really serious stuff for people. If they can really understand what's going on, they think they can actually predict the future. So the model was used for a very long period of time. This is what we call the geocentric model of the world. But the geocentric model of the world, it looks like an incompetent work. Why do I say that? You would have the Earth at the center, the moon going around it, Venus going around it. But if you study Venus moving through the night sky, you would see it do this rather interesting thing where you see the star Venus move like this, and after a while to do this loop like this backwards, and then go on again. This motion is called a retrograde motion. So you see a star go, the stars don't move like this across and then return to the same place, and you call it a year. What they do is they'll move, make this loop, and then move again. So to account for that loop, Ptolemy had to say, not only are these planets going around in a circle, but that there's a nested circle again on that circle. So I can explain the fact that it looks like it's going back at some point in time. Then it was ugly in the other sense that there seemed to be a special rule for these inner planets, that's Mercury and Venus, and then a separate set of rules for Mars, Jupiter, Saturn, right? Which was that for Venus and then Mercury, they always had to be found on the straight line that connects the Earth to the Sun. You could never find Venus standing somewhere here and then moving. No, you would never see that. It's always very close to the Sun, right? And Ptolemy couldn't explain this, so he just said it has to always be like this. That's why I draw this line through it, okay? But then came somewhere in the 15th century, this fella here. I think he's a Polish astronomer, and then I think a priest as well. So having studied the model that I showed you earlier about how these stars, what we call the wanderers, or aka the planets, move around the Earth, he thought the picture was ugly. And for purposes of beauty and simplicity, he assumed that we rather place the sun at the center, and then all the other planets are in concentric circles around it. And you can tell that once you do this, you make this arrangement, you have to now say this Earth is also moving around in its orbit. But that's where the trouble comes in. Because we are here, and I can swear that this place is stationary, right? But then Copernicus is telling us that no, it's not. It's actually moving around. Moving around. And it does this job in a year. So it moves from here, goes around, and comes back in 1 year. So when you say I'm a year older, you're trying to what you're really saying is that you are back to the same location that the Earth was in when you were born. That's what you're saying. So after a year, it comes back. And when you're celebrating your birthday, maybe you were born when the Earth was at this point. So when you're celebrating your birthday, it means for some strange reason, when the Earth gets here, you get all excited. I mean, we don't know why, but you really, really get excited. Right? So that's what it means. But if you were born on Venus, right, then, I mean, for some strange reason, when it sweeps around and comes back here, you also get excited on it. But the funny thing about the Venus year is that Venus takes, if I remember correctly, something on the order of 200 days. So it's less than a year, right? So in less than a year, you'll be celebrating your birthday very rapidly, right? That sounds like fun, right? And if you were on Mercury, you'll be celebrating your birthday every 3 months. So every 3 months, you're celebrating your birthday. For no reason, once the planet is at a particular point in its orbit, you get excited, right? So this is the Copernicus model of the world that he presented to us. But he didn't present this model of the world because it had any real advantage over the other model of the world, because there were things Copernicus couldn't answer. Like if the Earth is moving, right? And he also said it's not just moving, it's also rotating, right? So if it's rotating, that's how come you get day and night. And if it's moving around, that's how come you get a year, right? So that's how we set this thing up on a calendar. So, but he couldn't explain when he was asked by the people who didn't believe what he was saying. He couldn't explain why we don't feel a gush of wind blowing past us because the Earth is in motion, right? And I can say that if I toss this object into the sky, you don't see it fall behind me, like we all think if something is rotating. Well, if the thing is rotating, it means at the time it left your hand, the Earth was in a different position, so or forward, right? So it should have fallen behind you. But we all know that when you throw something, it comes back. At least if you throw it well, it comes back into your hand. So he couldn't explain that, but because this was beautiful and helped him conceptually capture what was happening with respect to the planet, he was like, I like this idea. And if not for anything, beauty is something we really need to pay attention to, right? So I'm not sure why, but he doesn't publish his understanding of what is happening till later on when he's about to die. I'm sure because he can't answer the question, so he'd rather make sure that you guys will try to address it when he's gone. Now, so after Copernicus, there was a long-ranging argument, heated argument. Which is it? Is it this? Is the sun at the center, the Earth at the center, or the sun is at the center? Which is it? Because these are two different schemes of how the world works. And depending on who you are, you might think it's this, because you can't understand why the Earth should be moving or rotating or anything like that. And if you think for beauty reasons, then you might think, oh, maybe it's really like this, right? So this argument kept going on. And when this character comes into play, Tycho Brahe, who was a very rich nobleman by then, and he was supposed to go and study law and I think philosophy, right? But when he was young, a very interesting event occurred, which was an eclipse. So a few days before the eclipse, they were told that an eclipse will occur, and this particular day is when it's going to occur. This is going to last this long. And this is what you are going to see. And indeed, it happened. And ever since then, he fell in love with the stars and couldn't go on to study either philosophy or law or whatever he was told to go and study. But at another point in his life, he witnessed another interesting event, which was the planets, that's Jupiter and Saturn, were supposed to be aligned, right? He saw them in the night sky aligned, as in they were in the same location in the night sky. And when he looked at the tables that Copernicus had published and the tables that Ptolemy had published, Ptolemy was off by about a couple of weeks, and Copernicus was off by a couple of days. By off, what I mean is, they all, after telling you that this is how the world works, they printed a big table, right? That will tell you where this planet will be located, when it would, where this planet will be located, where it would be located, and over the course of years into the future. So you could always observe an event in the real world and then compare whether in the table it said this will happen in the table, just to be sure that the mathematical schemes that they have employed are very accurate. So he observed that when he saw this Jupiter and then Saturn aligned in the night sky, the two tables that were presented by Ptolemy and then Kepler were out of date. So it's like, nah, these tables are not accurate. So he set out on a life mission of making sure that he would devise as accurate as an instrument as possible. And mind you, he was making these observations without a telescope. So he was looking through a hole and at the night sky and then check to see whether everything is aligned, measure the angles, and he did this over the course of 20 years, accumulating data on all the planets, right? All the 5 planets that were known by then. And he was accumulating all of this, just so that he was hoping that if he were precise enough, he would be able to settle the difference, whether it's really like this or it's like this. So he gathered this data, which is an interesting point in the study of science, because it tells you that if two people are arguing about something, don't just keep arguing. Say, let's go and measure what we are talking about very carefully, right? So he's the first person to propose that idea. So he went ahead to measure the data very carefully and got this huge Excel table with a lot of information in it. But like all of you know, if you don't have either a Windows computer or an Excel application, it's hard to really make sense of a large body of data, right? But so he couldn't really make sense of this. And then he got a mathematician who was also an astronomer, but he had a poor eyesight, so he couldn't look into the pinhole camera and then carefully measure where the planets were. Rather, his job was to take the data that had been accumulated by Tycho Brahe over the course of 25 years and then analyze it and find out what is the underlying rule, right? Again, this is because he's motivated by a pattern-based approach to the world. What is the rule that all these planets that are moving in the night sky, these little dots that don't sit still and move around, what is the rule they are all following? So he also studied this problem for quite some time. I'm surprised he studied for as long as he did. But he did, and after close to 20 years, he finally triumphed. And he came up with what looked like a very ugly picture. At least if you are somebody who takes the Greeks seriously and you believe in mathematical purity and all of those things, you would be appalled by the picture he presented. Because he said it is not that the planets are moving in circles, but rather that they are moving in ellipse. For many of us, if we look at it like circle, ellipse, hey, boo, boo-hoo, what's the difference? But for the mathematicians, there's a radical big difference. An ellipse is a different animal to a circle. They are two different animals. Although they look alike, to a mathematician, they are two different things. For a circle, it has this one center, and every other point on the orbit is the same distance away from it. Whereas for an ellipse, it has what we call two foci. That's 2 points around which any object, right, is the same, the distance from that object to those two foci is always constant. And that's how you get the ellipse. So it's a radically different thing. And then the sun is not located on both foci. So there might be a foci here, one dot here, there might be another dot here. But the sun is always located on one of the dots. So that was the first observation. And all the planets do this. They are all moving in ellipses. For even a comet is even strange because its ellipse is really elongated, so it looks like this. It's like a squashed circle. So that's how it looks like. Then he came up with another interesting observation. Mind you, these are all mathematical observations. I'm explaining them in English because that's the best way to get the ideas across. But in essence, he's really talking about very precise mathematical quantities here. So he said he noticed that the time it takes a planet to move from this point to this point, when it's very close to the sun, and then the time it takes it to move from this point to this point, when it's very far away from the sun, are the same. So over the course of 6 months, it will move this distance, and over the course of 6 months, it will move this small distance. What does it tell you? It tells you that these planets don't move at the same speed through their orbit. What happens is that when they are here, when they are close to the sun, they move very rapidly. And when they are further away, they move very slowly. So you have this interesting behavior where a planet will come this way rapidly and then slowly move again, rapidly and then slowly move away. So that's what they kept doing. And he didn't understand why. And then there's the other curious observation that the time it takes each planet to go around the sun is proportional to how far away it is from the sun. So the further the planet is, the longer it will take it to go around the sun. Those are 3 of the rules that he came up with. And this is because Tycho Brahe had gathered enough data with precise instruments for him to carefully study it and then deduce what the underlying patterns were. So all planets do this. From this point onwards, he had a very precise mathematical rule or formula by which he could calculate where the planets were, right? So that was beautiful. Wow, I have this nice system, and it can tell me where the planets are. It can tell me when an eclipse will be located. And even for the astrology, people believe in astrology and all of that, it's even more interesting because it can tell you a little bit about the faith, your faith, as in what's going to happen to you in some time from now, or depending on when you were born, which I think is an interesting idea, but stop people from believing it. So from then onwards, right, it still wasn't clear. Copernicus told us that the Earth is not at the center, rather the sun. But the orbits he employed were circles, so he couldn't get the right answers for where would you locate a planet at a certain point in time. And Kepler came and told us with a very beautiful mathematical rules, 3 of them, the ones we just saw, where they are going to be, right? But still it was difficult because there wasn't anything in the world that could split the difference between these 2 pictures, right? There wasn't anything. So you just have one system of the world that says the Earth is at the center. It gives you beautiful answers, good, accurate calculations. There's another system of the world, which is the Copernican view of the world, which was further advanced by Kepler, which gives you a very accurate picture of the world. So we're like, which is it? I mean, I have 2 beautiful mathematical theories, and they all tell me what is going to happen. They don't differ. They don't have any differences. I mean, as far as the ordinary human eye can tell. Then, at that point, this individual comes into the picture of our discussion. I don't know whether any of you recognize him, but that is the Italian astronomer Galileo. Galileo's chief contribution here is that we should stop using our naked eyes, right? But that's not what happened. He didn't say that. But his contribution is that he got a certain tool, which is a telescope, that would help you see things beyond what your ordinary eyes can help you see. And when that was done, we were now in new, uncharted territory because he saw really beautiful, interesting stuff. And one of them was this. This is a drawing from his notebooks on what he was observing whilst he was looking through the telescope at the moon. And for the first time, he started seeing craters on it, seeing mountain ridges, and a whole lot of lowlands and stuff. And I was wondering, what is this? Because the picture of the world he inherited was to say that the heavens are perfect, right? The things that happen in the heavens are perfect and follow heavenly or what you might call celestial laws. And then the things that are happening on the earth is because of the corrupt nature of man. So we have decay, we have death, we have mountains and valleys and all of those things. So when he looked at the moon and saw all of these objects, he was shocked. Like the heavens, they have moons and mountains, right? So he was shocked. And then again, he turned his eyes at the telescope and looked at the sun, and then he noticed that there were dark spots on it. And like, I thought this object was supposed to be perfect and without blemish. Why are there dark spots on the sun? You and I wouldn't see it unless we have a telescope. So another beautiful thing he did was to study this sunspot over the course of weeks and a couple of months, and noticed that the pattern kept changing. This pattern keeps changing. So first you see it in the middle of the star, you see it halfway here, you see it there, you see it at the edge to disappear. After a while you see that pattern here, and then you see it here, and then the same thing kept happening. What does this tell you? It tells you that this ball itself is spinning on its axis, and what you see is moving across the surface. So that's also one startling revelation that he made. And then he looked at the night sky, and then he was surprised to find out that apart from the stars that you could ordinarily see with your eyes, there are a great many sets of stars that you can't see. But if you look through the telescope, you start seeing them. And he was amazed, like, wow. He's seeing stars that not even the Greeks or the Babylonians or any other civilization who had studied the skies had seen. Then he turned his attention to Jupiter. I'm sorry for this image, but I think the projector has blurred it up a bit. But when he looked at Jupiter, right, this Jupiter, when he looked at it, he saw 4 other stars close to Jupiter. So he thought, oh, Jupiter has an interesting set of stars around it. And if you didn't have a telescope, you wouldn't see it. So he looks at Jupiter again after a course some weeks and notices that these 4 dots keep changing. And like I just told you, whenever you see a star changing across the background, you know that it's not a star, it's actually a planet. Or in this case, they are satellites of Jupiter, or what we now know to be the moons of Jupiter. So those were some of his revelations. But this one was also particularly curious because for the first time he saw an object in the solar system that had other things going around it that wasn't the Earth. Because if you believe in the other picture I was telling you about, the Earth-centered model of the world, it means everything in this universe is going around us. But he saw with his telescope that there are things that are going around other objects that are not the Earth. So it made him more suspicious of this whole idea. And then he was asked by one of his students that what would you see if you look at Venus? Because when you look at Venus, you could really spell the difference between the Earth-centered view on the world and then the Sun-centered view on the world, based on what phases of the moon you would see. So in the Earth-centered view on the world, you would notice these phases, whereas in the Sun-centered, you notice these phases on Jupiter. And lo and behold, when you look through the telescope, he saw this. So from there on out, he knew that the Copernican picture of the world was the accurate model on the world. From there, we go to Galileo, right? Galileo, after studying the heavens, wanted to understand what happens when objects are moving on Earth. That was what he wanted to understand. What happens when objects are moving on Earth? And he carried out this rather beautiful experiment where he takes a ball on an inclined plane, drops it, and he sees the ball roll down. And then when it gets here, it rolls up again, because when it was here, it was moving at a high speed, so it rolls up again. And notice that the ball rises to the same height that he left it. So if he left it at a higher height, it rises to a higher height on the other end. And then he declined the inclined plane, as in he reduced the angle. And notice that the ball will now have to travel a further distance before it gets to the same height, right? So if you decline it this way, the ball will have to move further, right? So he was wondering, what happened if he just brought this bar down? Would the ball keep going, hoping to get to the same height, right? And that was his chief discovery, that when you don't touch an object, or if there's no friction or air resistance, an object will still keep moving and moving and moving and would never stop. Now, as hard as this is to believe this is actually the case. So suppose I pull this chair. One thing is that once I stop pushing it or pulling it, it will stop. And that's what we all think. But Galileo's understanding was this, is that this chair stopped because it was in contact with the floor. So if you had smoothened this floor and put a knife, you had, polished the whole floor, if you push the chair, it should keep moving. It will not stop. So that was his contribution to our understanding about how objects move on Earth. Before him, people used to think objects only move because someone is applying a force on it. Now, so you might say, okay, what's the big deal? Galileo has told us that the Earth is not at the center because of what he saw with the waxing and waning of the moons of Venus, right? I mean, Venus itself. So that's not a big deal. We had settled that issue. And he also told us that when you push an object, it should still keep moving and be moving and moving and never stop, right? That's what Galileo told us. But then this man comes to play. I don't know who knows this. Who knows him? Okay, so this is Sir Isaac Newton. I'm sure everybody has heard of him. And the popular story we hear is he was sitting under an apple tree. An apple fell on his head and he came up with gravity. I know, because ever since the story was told, a great many children have been trying to discover new things by sitting under an apple tree. And I'm sure they didn't come up with the right answer. But let me just say that story is apocryphal. It's not true, and that's not how he came about the idea. So Newton's contribution, when we come to think about our place in the universe and what's happening and all of this, is simply this idea. He borrows two ideas. Or let me say, yes, he borrows two ideas. One from Aristotle, in the sense that says, when you have an object and you're not supporting it, what's supposed to happen? It's supposed to fall. And then he borrows another idea from, he borrowed another idea from Galileo, which is to say that when you push an object, it should still be moving and moving and moving and never stop, right? So he was trying to combine these two ideas. How could it be? Because if this is the thing, when I leave this object, what's going to happen? It's going to fall. When I climb up to a mountain and I leave this object, it's still going to fall. So it means things will fall wherever they are, right? Whether you're on a mountain or sea level, when you leave an object, it still would fall, right? So he was trying to find out, why is it that if things are not supported, would fall? Why is the moon in the sky? I don't know whether that idea has struck anyone. But essentially, we don't see anyone holding the moon. Unless you evoke entities that you and I can see, it means the moon is hanging mysteriously somehow. And that's what we are supposed to explain. So Newton's chief contribution is to say, suppose you fire an object at a low speed, what's going to happen? It's just going to move a little distance and then fall. If you fire it at a high speed, it's going to move further and then fall. But if you fire it at the right speed, it's going to keep falling. But whilst it's falling, the Earth is curved, so it will still not make it, it will not quite make it there, and still be falling and then falling and falling. So he explained that it is possible for an object to be falling consistently around another object without it ever getting onto the object. So in essence, the moon is falling. It is not that the moon is being held by a special set of forces that's up force and is holding it. But rather, the moon is falling. But like I told you, any object that is moving will keep moving and moving and moving. So it's falling, but the Earth is also curved. So it's falling around the curve like that and consistently. So consistently, the moon is falling. And that was Newton's contribution. And the idea was to say, if an object is going around another object, it means they have an attraction between them, because one is trying to pull the other towards it. And then because of inertia, it will keep moving forward. So that was Newton's contribution. But not just that. It is curious that Newton saw this happen to the moon, as in he tried to explain the moon. And he said, okay, the moon is literally falling, but because the Earth is curved, that's why it doesn't fall. And he's like, okay, fine, what about the planets? What keeps them in their orbits? right? Because until now, I've still not told you why the planets move around their orbit. Newton was the first person to realize that the planets are also falling, but they are falling around the sun and never hit the sun's surface because of the initial speed that they have. So all these planets are falling. And like Galileo told us, the moon also, Jupiter also has a couple of 9 planets that are 4 moons that are going around it. And they are all falling around Jupiter. So he was like, I can see this happening on the Earth, that an object on the Earth will fall down. It explains why the moon is in the sky, explain why the planets are in the sky. Then maybe this is not a local thing. It's not only things that are happening here on Earth. This was the first time when humans bridged the laws that were happening on Earth and then the heavens. Until then, you always look at the heavens and the sky as 2 different realms. There was things that were happening in the heavens, and then there are things that are happening on Earth. But since Newton, we now know that what happens on the Earth is not a unique thing. It happens across the universe. And everywhere you look, this pattern keeps on occurring. So Newton went on a limb and to say, I'll stick my neck out. I believe this is not a local thing, it's universal. So Newton's contribution was to say, all objects in the universe are attracted towards all other objects in the universe. But he made this bold claim from just observing a few things. And that's how science really progresses. You see a few things and you make large generalizations about them. Because if you are to say, oh, I only know about what I've observed, I will not say anything about what I've not seen, then it means you can't make predictions. Because when you make predictions, you are really saying there's something about what you observe that holds true beyond just the things you've seen and can help you tell about other things that you are yet to observe. So that was Newton's chief contribution to the world. So by Newton's time, we know the planets and every other object. So as I'm standing here, because Newton's contribution is to say all objects are attracted towards Earth, it means all of us are attracted towards each other right now and are also attracted towards the sun. So there's an attraction between this individual and this individual, and that individual and this individual, and every other individual over here. But why don't we feel that attraction? Because one would think, if there's this chair and I'm attracted to this chair and there's a force of attraction between me and this chair, then I should just see myself gradually gravitating towards the chair. But that doesn't happen. Because although there's a force of attraction, it's very weak. And it's so weak, it can't move a huge mass like me in that direction. And then again, there's the gravity friction problem. So that is one of the breakthroughs that we learned from Newton at this point. So then the question is, maybe Newton again is just a local phenomenon. It's something that has happened here, just within our ballpark. But if you look further, this is an artist's rendering of what we call a binary star system. That is two stars, or you can say 2 suns that are going around each other. In our universe, in our solar system, we only have 1 sun or star. And then by we I mean the planets are going around it. But there are other systems in the universe, even in our own galaxy, where there are stars that are moving around each other, held together by their mutual attraction. And that's what is keeping them in their orbit. So they are falling around each other. That's one way to look at it. And these objects are usually on a scale of roughly 4 light years apart. And for the people who have already explained it to, a light year is roughly the distance light travels in a year. And to date, we know light is roughly the fastest object in the universe. So traveling a distance of a light year is a really, really long distance. The furthest thing in our galaxy, in our solar system, is I think on the order of 7 hours away. So that's how far maybe a planet like Neptune is. But these objects, which are 4 light years apart, still move in accordance with Newton's generalization that all objects are attracted towards each other. Now, how true does this law hold over all scales? Because again, we've only observed it locally, seen it here on the Earth, on Jupiter, and then we've seen these 2 binary star systems moving around each other like that. Does this rule hold over much larger scales? And yes, indeed, It does. So the object we are now seeing, this large swarm is made up of stars, and these stars are falling around each other. So it's a large aggregation of stars that are attracted to each other in one huge assemblage. We call the globular cluster, right? And all these objects are still on the order of, I believe, 100,000 light years. I think it's 100,000 light years apart, right? And all of these objects are still falling around each other. Again, we can't now confirm Newton's contribution, but because of the distribution, we suspect that the same laws that Newton proposed are still holding, even on this large scale. And another object, the largest object we can see from Earth, is what we call the Milky Way galaxy. And this object is 100,000 light years in length. So from here to here would take light 100,000 years. Now, what was happening 100,000 years? 100,000 years, I think the human species was nowhere near building civilizations or anything that has the resemblance of culture in it. So if you are on Earth right now and you're observing a star on the opposite end of the galaxy, it in essence really means that when the star left its star, when the light left its star and then was motioning towards the Earth, if you are on the other end of the galaxy, the human civilization wasn't even in existence. And that's a strange and interesting fact about the world, that because light has a definite speed, we are literally looking into the past every time we are looking at objects. So these objects, we are not seeing this Milky Way as it is now. We are seeing it the time ago that this light came to reach us. And again, this whole Milky Way is held attracted to each other, all of it going around a central mass in the center that we call the galactic core, and the whole thing is spinning around it. Again, due to an attractive force, but we can't say definitely whether it's following Newton's rules or not. But I just want you to understand that this force of attraction still holds on time scales, space scales as large as 100,000 light years. And in this picture, what we have is the Hubble picture, deep picture. So the stars, the tiny dots you are seeing here are not stars. Again, the issue of scale always has to come into play. These are not stars, rather they are galaxies. That's large assemblies of stars. Each dot you are seeing is a galaxy. And depending on some of them, for example, if you take this one, if you per the astronomers, some of these objects are as far as, you could say, 12 billion light years away. In essence, you are seeing this object as they were 12 billion years ago. And who was here by then? Even our sun wasn't there when the light left that galaxy. So we are really looking at some of the oldest images in the universe. And even on this scale, right, where on this scale we are talking about 1 million light years across, even on this scale, we still have a force of attraction attracting this object. So you see that this funny thing where I leave this object and it falls to the ground, this rule, this law, this force of attraction expands well across and into the whole universe. So it's not a very local thing, it's a thing that transcends the entire universe. So there's always, all objects in the universe are always attracting each other in one, continuous mutual attraction, where it's not just only stars attract stars, but stars attract globular clusters and supernovas and every other object. Once you are an object that has mass, you'll be attracted to another object. Only that the further away you are from the other object, the weaker the force of attraction. So we are at the very end of the lecture, right? Where we've moved from understanding that the Earth itself is a sphere moved to understand how the objects move around our solar system to our galaxy, and we've seen the larger structures in the universe where we're seeing a large aggregation of galaxies, right? But I want to end on this interesting note, right? This picture represents what I believe most biology students will call the red blood cells, right? So this is what makes our blood red and then moves oxygen from, let's say, our lungs to the rest of our body. And the chemists here will tell us that this is the symbol for iron. And you know we use iron for making steel and making farming implements and weapons and the usual. And then again, there's this other picture. What you are seeing here is what we call a supernova. This is actually not an ordinary star, but it is a star that has just gotten to the end of its life. So when stars finish consuming all the fuel, they collapse in one giant explosion. And that explosion is so bright, even if you are halfway across the visible universe, you can still see it. It is one of the brightest objects we know in the universe. But the interesting thing about this explosion, the supernova explosion, is that when it does explode, the stars spew into its surrounding space elements. So it spews, when stars are actually burning, they will first take hydrogen, burn it, and then form carbon, nitrogen, oxygen, and then they'll be forming every other element on the periodic table. Right? They'll be forming all those till they get to iron. Then when they get to iron, they can't burn iron again, and then they'll go supernova, and then the whole system will collapse in on itself. It will exhaust its fuel and then explode. And when it does explode, it will release iron into the surrounding environment. So interestingly, think about this though. These red blood cells can carry oxygen from one point in your body to another. But they do that largely because they have iron, the iron atom, at the heart of the hemoglobin molecule that's used for moving oxygen around. And then we have iron we use for building, skyscrapers and tools and all of that. But in essence, the iron that runs through our blood, all of us, our blood, actually came from a star that died and released its iron into the surrounding space before our sun was formed. And that's why we have iron on the earth now. And that's why we have iron in your bloodstream. So in a very intimate way, you are connected, all of us, connected to the very nature of the universe itself. Not in some woo-woo mysterious sense of the word, but in a deep sense of the word. That's to say, the very material out of which we are constructed was formed in the center of stars. And when they died, they were made available when our sun was forming. And then thus, when life evolved here, it took advantage of that element, iron. Thank you very much.